Hey everybody, this is Larry. This is April 26th, Friday evening. Trying to do an extra lead code problem. One that I haven't done before, so let's take a look. And oh, we have a hard one. I guess I've done too many mediums because I feel like recently the RNG problems are all hard. Let's take a look. 1788, maximize the beauty of the garden. Already sounds like a dynamic programming problem, but we will see. There is a garden of n flowers, and each flower has an integer beauty value. Okay. Flowers are arranged in a line. You're given integer array flowers of size n, and each flower sub I represents the beauty of the I flower. A garden is valid if it meets these conditions. The garden has at least two flowers. The first and the last flower of the garden has the same beauty value. Okay. As the pointed gardener, you have the ability to remove any or possibly none flowers from the garden. You want to remove flowers in a way that makes the remaining garden valid. The beauty of the garden is the sum of all beauty of the beauty of all the remaining flowers. Return the maximum possible beauty of some valid garden after you have removed any flowers, possibly none. There's a negative numbers. 10 to the 5th is n, so so maybe it is not dynamic programming. Okay, so we can have -1 as a thing, and you remove -2, right? Let me think about this, right? So I mean, I think the first idea is going to be that we should be able to brute force. So okay, so there are two concepts, I think. One is that we should be able to brute force every garden, and by that I mean the number, right? And by number I mean like ones and twos or whatever, right? We could brute force one and then twos and then threes. And the reason why you could brute force that is because the only n of them, if you pre-process them correctly, you should be able to just do all of them. It'll be linear time as long as you do it fast. And then the second thing is an obvious greedy. You want to keep all the files that you can, and then and remove all the negative numbers, right? I mean, you have to keep some negative numbers, but we'll talk about it when we get there. So okay, so then here, I think I'm going to solve this more. I mean, I think, to be honest, I know how to solve this now, but I want to go over the thought process about how to break it down, because I think this is an interesting problem in that, and this is something that I think a lot of people struggle with when they ask me how to solve Q4. Maybe not this one. I think this is a slightly easier hard, but still, it's just this idea that you have like a checklist of 3 or 4 things, and you have to break them down and figure out how to solve them, right? Is what I mean. Okay, so first thing is that we can brute force all the numbers. There are n of them, so at worst it'll be O of n, right? So at worst, so let me rewrite this. What I mean is that there are n of them, so we have to be able to do them in O of 1 each, or O of log n each to be fast enough, right? Okay, and let's say we are able to kind of, get the beginning and the end of every number. Then now we have to get then now we can use greedy, right? Just sum up all the numbers. But for each number, maybe I don't think I said it explicitly, we can use greedy, just sum up the number in between the first appearance and the last appearance, right? But we also want to, in the same greedy, we want to remove or not add the negative numbers. Obvious reason. I mean, I think that's reasonable. So okay, So each of these things are kind of, I think now we have the observation and the ideas, and the rest of it is kind of just like having the experience to, I mean, and maybe some of these ideas, and we kind of already, like, you could say maybe there are 3 ideas here already, and you have to figure out how to do them quickly and all these things. And the thing about these ideas, right, is that with practice and experience, well, you know whether they're possible or not. For example, if I'm like, oh, I could brute force all the numbers, but I don't think there's a fast way to do it. Then it doesn't matter if you have this idea, because you can't do it, right? Like if the only way to brute force is O of n, then this is gonna be n squared, and n is 10 to the 5th. N squared is gonna be too slow. No good, no Gucci, right? No bueno. But because like I said, like I think about it for a second, and then I'm like, oh, I know how to do this part, or I know the data structure, I know how to, or whatever it is to do it. So then we can do it, right? So let's break it down, right? So for this one, for example, I'm going, okay, brute force all the numbers. I mean, I guess that's simple. We can put it in a set or something. It doesn't really matter. But then for each number, what do we do, right? So okay, let's do that for a second, right? So then now maybe we can say scene. I don't know, numbers. Let's just put numbers, right? And then now for f in flowers, numbers dot add f. Okay, and then now we can do like for f in numbers, then we can pre-process it, or not pre-process, just like for this number do the greedy, right? All right, but then now what are we doing? Okay, so then the next step maybe, okay, now we have a set, and then we can do this. So then now it should be, and you can see that this is linear so far, right? Because numbers is going to be a smaller set of flowers, so that's fine. But we have to figure out how to do this. Okay, so then for each number, what do we do? Each number, we want to find the first and the last appearance. Oh, okay, so let's actually keep track of the first and last appearance of each number. Okay, so I mean, numbers as a set doesn't really make sense as much anymore. So then maybe we could just, because, well, I mean, it maybe makes sense, but you can still use an auxiliary thing where, first and last to show the first and last appearance. Because in a greedy kind of way, just to be clear, I don't think I made this clear. In a greedy kind of way, you want to add all the, you want to add as many flowers as possible, as long as they're positive, which we put in the next point, but we'll get to it in a sec, right? You want to add, you want to get as many as possible, which is why we want the first and the last, because, well, that'll just give us a bigger garden, well, using their terminology, right? Okay, so then now here we can write first, if f is not in first, then first of f is equal to index, right? We have to get index. And then now, and then last we always update because it overwrites the last one, right? You can write it in a different way, but that's the idea. And then now, of course, one thing that you notice is that numbers now do not, numbers contain information that is already found in first, right? Because all the keys of first is the things that live in numbers. So then you maybe remove it. It doesn't really matter that much, this part, to be honest, but I just want to show you how, if you see some people doing that way, it's because they always saw that, oh, we overlap usage in how we do things, so we could reuse the keys of the first dictionary and then do it this way, right? Okay. And then now here we want to sum up all the numbers from the first and the last. So then now we have maybe first index is equal to first of f, last index equal last of f, right? I know that I think it gives you keys by default, but I always like to write it explicit because some languages are weird, and I don't know. I know too many languages in my head, and I just don't want to think about it. But that's fine if you do. It doesn't matter. And then now we can write something like total is equal to 0 for index in range from f index, L index plus 1 to be inclusive. Total we add what is it, flowers of index, right? And of course we want to also and then in the next one, and we always said this already, we don't want to include negative numbers, so we only want to add it if it's greater than 0, right? So then now we have totals here, and we want to maximize the beauty, so we're just going to say best is equal to 0, And then yeah, if total is greater than best, then best is equal to total. You know, regular normal stuff, right? And we're mostly done, right? Kind of, almost, hopefully. Well, at least get the right answer here. I did miss the case where it has to have at least 2 flowers, so I did miss that. So then here we can write if first index is equal to last index, then we only have 1 flower and we continue, right? Oh, and the best, because we can't have negative values, so this should actually be negative infinity. So that is a silly mistake. But this is why we test things, in any case. And now you can see that is, because this total is, Oh, because you have to count the edge of these flowers. So okay, so this is a little bit off because then now you actually, because of this conditional, I'm filtering out the borders or whatever they're called, right? So then here, let's just say we can skip the first one, skip the last one, and then set total is equal to f times 2, right? One from the beginning, one for the end. Okay, there you go. But unfortunately, it's going to be too slow. Why? I mean, we said it, we have it here, right? I mean, I guess I didn't say it explicitly, but this is going to be O of n, number of iterations, that's fine. But then here can also be O of n, right? And of course, this is now n squared. N squared is going to be too slow, right? So then now what can we do? Well, we can notice that this is, the query that we get a lot is that we're always getting a sum of a subarray, right? With a caveat of less than 0, but we can talk about that. But basically, we're getting a subarray sum, right? And for me, when I want to get a subarray sum repeatedly, and this is just experience and practice, it's just going to be prefix sum. I'm not going to go over prefix sum in way much detail. I have talked about prefix sum very often in places, so I feel like I don't want to get into it that much. But I just want to show you how to break it down, because now you have 3 things, and then you're like, okay, well, I have to solve this other problem of this speed and doing it fast enough, the summing up part, and then I have a tool for it. It's called prefix sum, so let's just use it. Like I said, I'm not going to get over prefix sum that much for this particular one, but we will have to do it. So yeah, so prefix is equal to 0, right? And then now for f in flowers, we can do prefix dot append the last element plus f, right? So this is prefix sum, and then now we can, and I know that this is not quite whatever, but here now this is just the sum between f index plus 1 and l index minus 1 inclusively, right? So then now we can replace this with a prefix sum. Again, I'm not going to go over it that much, but you know, I just want to show you for this video, I want to show the problem solving process and not the details about the algorithms. But there are a lot of prefix sum problems that you practice, and I actually do recommend you have a good grasp of it in general, right? So then I have L index, yeah, minus prefix of F index, I think. Plus 1, yeah, I think that's right. This is not going to be right. Why? Because we do not remove. Well, I think this is wrong anyway, to be honest. I think I'm off by 1 somewhere. But x plus 1 yeah, this is definitely not what I would have expected. I think I'm just off by 1. F index plus, oh, is this plus 1 because it's plus 2? Okay. Yeah, so now this is still wrong, but more correct than I had, because I just, yeah. And I'm not going to go over this because it's prefix sum, but basically it just gets the sum between this. And as we said, we want to implement this, but what we implement was this, right? We don't have the if statement. And it turns out that there's an easy way to do it, which is that just, you know, f is equal to max 0 of f, and then that's pretty much it. Yeah, basically it's saying that if it's negative, then we just remove it, and removing it is the same as adding 0 into the prefix sum. So then you can do that. And yeah, that's pretty much it. And this gives you the prefix sum from that index. And we already took out the edges, so this could be negative, and that's fine. And then everything's good. So let's give it a submit, and hope I don't have a silly off by one thing. And yeah, that's pretty much it. And the biggest thing about the prefix sum is that now this is O of 1 and this is O of n. So that means that we do this in O of n time. Here is O of n time for the prefix sum. Here is the pre-processing, also O of n time. And that's pretty much it. You can also rewrite this in any number of ways, but I don't know. This is the way that I have it. Like, for example, you could have done it in one. You could do it in one loop, really, to be honest. But I like to kind of separate it out for visualization. So hopefully that makes sense. And this is basically it, right? You basically start with all the ideas that you have, and sometimes it takes 3 or 4 steps to kind of get there, maybe even more for some of the harder problems. And each of these steps have kind of like, well, one is that, for example, in greedy, you have to prove it, kind of. This one is a little bit easier to prove. You don't add negative numbers to maximize the number. Okay, fine, right? But yeah, you have to have an idea on all of these, and some of them will take different ideas and different implementation, right? So yeah, that's all I have for this one. Let me know what you think. This is linear time, linear space, and that's all I have for this one. Thanks for watching. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.